All right, we're back with velocity time graphs. So I'm going to sketch one. You might notice it looks the same if you watched my other video for the position time graph. It's because I do that intentionally. So it'll look like this. This being 1 second, 3 seconds, and 4 seconds. This being 5 and -8. It's not exactly the same, but it's pretty close. Here's the most important thing you need to know as we move on to velocity time graphs. They are, in every single way, completely and totally different. If you want to ace your first kinematics test, if you want to get good grades on the AP Physics 1 test, the very first thing you need to know is that whatever the rules were for position time graphs are out the window. They're over there. We don't care about them anymore. Everything is completely and totally different. All right, so starting with position. Ooh, that's a terrible marker. I'm so sorry. There we go. We can't find it. That's the fun part. We can't find it. We absolutely cannot find it, okay? Unless we have initial position. It's not on this graph anywhere. What we're about to talk about is that we can find distance and displacement, but if I don't know where I started, then distance and displacement can't help me figure out where I am now, right? Displacement is x minus x naught. So if I know I was displaced 10 meters, but I don't know where I started, I still can't figure out where I am. So unless you're told in the question, and the initial position was at 0, or and the initial position was 10 meters. If I have that information, then I can easily figure out where I am now. I'd be at a position of 20 meters. But unless I'm given that information, position is not on this time graph at all. At all. It has to be additionally given in a different part of the question. You cannot find it using just this picture. Let's talk about distance and displacement. We're going to do displacement first. Displacement is the area under the graph. Technically, it's between the graph and the x-axis. That's technically what it is. So it would be this area and this area, and that's a little tiny triangle, and then this guy. That's the area under the curve. I'm going to use geometry to find it. 1/2 base times height. Sometimes you get trapezoids, but that area is on the equation sheet, fun fact. I typically just break it into triangles and rectangles though. Stick with the easy stuff. But displacement is the area under the graph. Use the area from geometry that you know how. Okay? Keep positives and negative areas and add them all together. So if we do this as an example, I want to know the displacement in the first 4 seconds. Okay, well, for this first section right here, I have 1/2. My base is 1 second. My height is 5. For this triangle, I have 1/2. My base is 2 seconds, and my height is 8. Negative 8. Right? 1 to 3 seconds, height of -8. Plus, I'm going to say that happened in we'll call this 3.25 seconds to make life easy. So plus 1/2, I'm up to, we'll call it 3 in 2.5 seconds. And then I have a rectangle. So from 0.25 seconds to 4 seconds, I'm at 3.7. Okay. If I add that all together using a calculator, 0.5 times 5 minus, this is negative, that one's negative, 8, plus 0.5 times 3 times 0.25, that's ugly, plus 3 times 0.75. Negative 2.875 meters. That's how far I've been displaced. The negative's important because it's displacement, so it can be positive and negative. When I was having a positive velocity, that was above the x-axis. We'll talk about that in a second. Above the x-axis means positive velocity. I change direction when I go under the x-axis. So I did some of this going in a positive direction and some of it going in a negative direction, which means my displacement nets between those two. I have to add the positive and the negative, and I end up with this. Sorry it wasn't a pretty number. I try to do better. All right. For distance, it is, again, the area under the curve, but keep everything positive. You can think of it as the absolute value. I keep everything positive, because remember, distance doesn't care which way I'm going. If I traveled it, I did it. So all I have to do is get rid of that little negative sign there and add this all up again, which is 13.125. So that's how far I actually went. So distance is still area under the curve. I just ignore negatives, all positive, because distance is scalar. It only goes one way. All right, I was going to say questions, but there are no people in this room. That's funny. All right, next up, direction of travel. It's not the slope at all. It's above or below x-axis. Again, the rules completely change. The most common AP Physics 1 issue at the very beginning of your year is this kinematics graph where you're like, okay, but the slope is negative, so I'm moving in a negative direction this whole time. No, that was a position time graph. This is a velocity time graph. On a velocity time graph, direction of travel is, am I above the x-axis or below the x-axis? That's it. Next up, speed. Speed is the magnitude of the y value. So for example, what is the speed at, I'm going to call this 2. I know it's not. I get that, okay? But I'm going to call this 2 seconds. Well, my y value is -8. I just need the magnitude of that. So my speed is 8 meters per second. If I do what's my speed at 0 seconds, my initial speed, right? At 0 seconds, I'm at 5 meters per second. That's my y value. So that is my speed. Velocity is the y of the, this should say y value. It's the y value, whatever it is. So if I want to know what is the speed, what is the velocity at 0 seconds, it would still be 5 meters per second. At 2 seconds, now I can say it's -8. It's the whole thing. I don't need to make it positive. It's velocity, so I can have negatives. So it is the whole thing, -8 meters per second. It's not the slope. The slope at 2 seconds is like unfindable, right? Because we're changing slopes. So it's not the slope. Don't make that mistake. All right. Speeding up. or slowing down. For this, we're looking, speeding up is getting closer to the x-axis, or sorry, further from. Ooh, I'm doing that backwards. Getting further from the x-axis, and then slowing down is getting closer to the x-axis. This is important. If I'm getting closer to the x-axis, that means that my speed is going from 5 to 0. So I am slowing down. If I'm getting closer to the x-axis, that means my speed went from 8 to 0. So I'm slowing down. I'm going from some other speed closer and closer and closer and closer to 0. So I have to be slowing down. It is not, am I going up or am I going down? That's not what it is. Because here, I'm going down the whole time, but I'm slowing down, slowing down, slowing down. Now I'm speeding up, speeding up, speeding up. It is, am I getting closer to or further away from the x-axis? Okay? So for example, at 4 seconds, am I speeding up or slowing down? I tricked you. I like doing that sometimes. At 4 seconds, I'm not getting closer to or further away from. I'm staying at the exact same speed. I have constant velocity. Ooh. So constant velocity right there means that I'm not getting closer to or further away from. I'm staying exactly where I am. So at 4 seconds, I wouldn't be speeding up or slowing down. I'd be at a constant velocity. Let's try at 1 second. No, not 1 second. Let's try at 2 seconds. Sorry. Oh, 2 seconds is bad too. I do a lot of these. Okay, at 3.25 seconds. Right here. I'm slowing down. Well, no, I'm not doing, wow, all of these times are bad. Let's see. At 1.5. At 1.5 seconds, I am speeding up. I am going away from the x-axis. Ooh, that was a rough one to find an example of. Bad graph. Okay, going away from or towards. Remember, throw out all the position nonsense. It's gone. Last thing, acceleration. The nice thing is acceleration is the slope of this graph. It is technically still combining velocity and speeding up and slowing down. Right here, my velocity is positive, and I am slowing down, so I should have, if I'm slowing down, my acceleration is opposite my velocity. I'm slowing down with positive velocity, so I should have negative acceleration. Boy, howdy I do. Negative slope means negative acceleration. Awesome. So let's do another example. Acceleration at, let's say, 3 seconds. Well, it's positive because I have a positive slope. But the question could ask, like, no, actually, what is the acceleration? And okay, that's fine. I'll figure it out. So my change in velocity, right? My change in velocity is v minus v naught over t. So my initial velocity down here was -8. My final velocity up here, we're calling that 3. And that took from 2 to 3.25 seconds. So that's 1.25. Now I'm going to have to use a calculator. 3 minus a -8 divided by 1.25. Now, technically what I just found was average. acceleration. This is the average acceleration from 2 to 3.25 seconds. Just like on the position time graph, if I calculate it, it's an average. That is the average acceleration from 2 to 3.25 seconds. It is also the instantaneous acceleration at 3 seconds. Why? Because the slope doesn't change. Since the slope this entire time is the same from 2 to 3.25 seconds, that means that if it's 8.8 on average, but it's the same everywhere, then at 3 seconds, this would be instantaneous. So average, if you had to calculate rise over run, instantaneous if you have constant. Slope. And that is the velocity time graph. We can figure out less information and it's slightly easier, so that's exciting. At least the video is shorter. Let's do acceleration at the same time while we're at it. I so thoroughly apologize for my cough. All right. Here's an acceleration time graph. In AP Physics 1, this is as exciting as they're going to get for the most part. They could show you a linear graph for acceleration and ask you what it means. It would mean the acceleration is changing over time. Awesome. But that's literally the question they can ask. So, we cannot find position. We cannot find distance. We cannot find displacement. We cannot find direction of travel. We cannot find speed. And we cannot find velocity. Wow, that makes our jobs super easy. The only thing we can figure out is if, oh, no, not speeding up or slowing down. Oh, wow. The only thing we know is the acceleration. So in this case, let's say it's 5. The acceleration is 5 meters per second squared the whole time. Wow, that's super easy. So acceleration is the y value of this graph. There's actually one more thing we can find. We just can't, it's not on that list. It's a new thing. We have to be specific. We can find change in velocity. We cannot find actual velocity. Just like on a position time graph or a velocity time graph, we couldn't find position. I don't know what my starting velocity is. I'll know the change in my velocity, but if I don't know what velocity I started at, I don't know what I ended at, right? If I know that the change in velocity is something, let's say 10, but I don't know my initial or my final, I can't find either one. So I can't really find velocity. I can only find change in velocity. Change in velocity is the area under the curve. Velocity is a vector quantity, so if it's positive, I would keep it positive. If it's negative, keep it negative, right? So in this case, let's say this goes for 4 seconds. The area under my curve would be 5 times 4. So my change in velocity would be 20 meters per second. So I either sped up or slowed down 20 meters per second. I don't know. If I had positive velocity and I changed by 20, I sped up. If I had negative velocity and it changed by positive 20, then I probably slowed down. Heck, I even could have changed direction. I truly don't know. All I know is that my change in velocity is 20. Okay? These are the kinematic graphs. I'm going to finish up with something I think every AP Physics 1 student should know, which is what the pattern looks like. If this is position, bear with me, and I have a straight line or I have a curve, the next graphs are always going to have the same pattern. So if I have linear, then the next graph, in this case velocity, is going to be constant. If I have curved, the next graph is going to be linear. Let me make sure I draw that right. I was doing this wrong. That's a negative velocity, FYI. This one is flat to steep. Flat to steep with a positive velocity, so I'm speeding up in the positive direction, so that one. Make sure I draw the right ones. Just showing you the pattern, but like, make them right. So, then, for acceleration, if I have a constant, I will have a 0. Then for acceleration, if I have a linear, I will have a constant. So, linear, constant, 0. Curve, linear, constant. So this is for constant velocity. This would be for constant acceleration. And I can see that on the graph. Up here I have constant velocity. Down here I have constant acceleration. So again, if I have constant acceleration, I expect to see a curved, linear, then constant graph every single time. It might look different depending on what the motion actually is, but it will be curved, linear, constant. If I have constant velocity, I expect linear, constant, then 0 every single time. So that's a great way to match graphs if that's the question, right? What goes with which graph? Well, if I have a position graph that's linear, I'm only looking for a velocity graph that's constant, right? It's easy to pick up on that pattern. I might have to pick which one, but I can narrow down my options a lot. All right, how about it?